In the middle of Antarctica, on an endless field of blue ice. A black stone the size of a fist sits alone. There are no mountains nearby. No exposed soil. No rocky slope from which it could have fallen. For hundreds of miles, there is almost nothing but ice. The answer is above. So where did the stone come from? The answer is not beneath it. The answer is above. It fell from space. Antarctica is the best meteorite collection system on Earth. Stones that fall onto the ice can remain trapped there for thousands of years. The ice slowly flows toward the edge of the continent. But in some places mountains block that movement and force old ice upward. Powerful winds then remove snow and ice from the surface. Little by little, meteorites buried deep inside are exposed again, dark against the pale blue ground. This is why research teams return to these frozen regions year after year. And why more meteorites have been recovered in Antarctica than anywhere else on the planet. At first, they look like ordinary rocks. But when scientists measure their ages, they find something strange. Some are more than 4.5 billion years old. That makes them hundreds of millions of years older than the oldest intact rocks we have found on Earth. The best evidence for Earth's beginning, in other words, does not come from Earth. Our planet's own rocks are too young. Earth seems to have erased the record of its birth, while a small stone that drifted through space kept that record almost untouched. How can that be? How did Earth lose the first chapter of its own history? How can a meteorite tell us when the planet formed? And how can anyone reconstruct events that happened 4.54 billion years ago, when no ocean, continent, animal, or living witness existed? The first piece of the answer is inside that black stone on the Antarctic ice. So let us follow it backward, beyond the first ocean, beyond the first solid ground, beyond Earth itself, to a time when even the sun did not yet exist. But before we rewind that far, we need to check something. Is Earth's earliest record really gone? In a remote region of Canada's Northwest Territories, gray bands of rock rise from the ancient crust. This is the Acosta gneiss, one of the oldest known intact rock formations on Earth. Parts of it are about 4 billion years old. That sounds almost unimaginably ancient, until we compare it with Earth's measured age of about 4.54 billion years. Even this extraordinarily old rock misses roughly the first half-billion years of the planet's story. Imagine opening a history book and discovering that its first several chapters have been torn out. That is the problem geologists face when they try to understand Earth's birth. The planet is ancient, but most of its surface is not. Ocean crust is created, carried across the seafloor, and eventually pushed back into the mantle. Continental rocks are buried, heated, crushed, melted, and rebuilt. Rain attacks them. Rivers carry them away. Glaciers grind them down. Volcanoes cover them. Impacts shatter them. Over immense spans of time, Earth continually edits its own surface. That activity is one reason our planet is habitable. It circulates water, carbon, minerals, and heat. But it also destroys evidence. The same living geology that makes Earth such a dynamic world has erased much of the evidence of how the world began. Small bodies in space had a different fate. There was no rain to weather them, no ocean to dissolve them, and no system of moving plates to drag them into a hot interior. Many asteroids were heated, broken, and altered, but some primitive pieces survived with remarkably little change. The most valuable of these are certain chondritic meteorites. Inside them are tiny grains and inclusions that formed before the planets did. They are leftovers from the construction of the solar system material that never became part of a full-sized planet. Earth destroyed most of its first pages. Meteorites kept photocopies. That still leaves a difficult question. A stone does not arrive with a date printed on it. So how can scientists look at a meteorite and say that it is 4.5 billion years old? Because atoms can keep time. Some elements are radioactive. Their atoms are unstable, and over time they transform into other atoms at a predictable rate. Uranium, for example, slowly changes into lead. The process is called radioactive decay. It is not controlled by the seasons, the weather, or human opinion. Each radioactive isotope has a characteristic half-life, the time required for half of the original atoms in a sample to decay. Think of an hourglass sealed inside a crystal. The material in the upper chamber represents the original radioactive isotope. The grains accumulating below represent the daughter product created by decay. If you know the rate at which the sand falls, and you can measure how much remains above, and how much has gathered below, you can calculate how long the clock has been running. Real radiometric dating is far more complicated than turning over an hourglass. Scientists must determine whether the mineral remained a closed system, correct for lead that was present at the beginning, and compare multiple isotopes and samples. A rock may have been heated, fractured, or chemically altered long after it formed. One method can be misleading if the sample's history is misunderstood. That is why the strongest dates are not based on a single measurement. Different minerals, isotope systems, and laboratories must point toward the same answer. In the 1950s, an American geochemist named Claire Patterson used this logic to solve one of science's oldest questions. He studied lead isotopes in material from the Canyon Diablo meteorite, fragments of the object that formed Meteor Crater in Arizona. The meteorite had fallen to Earth relatively recently in geological terms, but the metal itself had formed near the beginning of the solar system. Patterson's answer was approximately 4.55 billion years. For the first time, humanity had a reliable age for Earth and the solar system. Modern measurements have refined the value, but the basic answer remains: Earth is about 4.54 billion years old. Even more precise clocks exist inside primitive meteorites. Some contain pale specks known as calcium aluminum rich inclusions, or KIs. These were among the first solid materials to condense in the young solar system. Their measured age is about 4.567 billion years. Scientists often use that date as time zero for the solar system, the closest thing we have to its birth certificate. So 4.5 billion years is not a number someone guessed by looking at a mountain. It is a number recorded inside atoms. The stones themselves contain clocks, and clocks found in different meteorites agree. Now that we have established the time, we can begin moving backward. Travel back more than 4.6 billion years and Earth disappears. The Moon disappears. The Sun disappears. Even the ingredients that will become those objects have not yet gathered into recognizable shapes. There is only a vast, cold cloud of gas and dust floating in the Milky Way. Most of the cloud is hydrogen and helium. Mixed through it are tiny grains containing heavier elements: carbon, oxygen, silicon, iron, and many others. Those elements carry an older history. Hydrogen was produced in the early universe. Much of the oxygen, silicon, and iron was forged inside earlier generations of stars. When some of those stars died, they scattered their contents into space. The iron in Earth's core and the oxygen in every breath were made before the solar system existed. For a long time, the cloud remained cold and diffuse. Then part of it began to collapse under its own gravity. We do not know exactly what triggered that collapse. A shock wave from a nearby exploding star may have compressed the cloud. Or the region may simply have become unstable under its own weight. Meteorites preserve traces of short-lived radioactive elements that may point to nearby stellar activity. But the exact opening scene remains uncertain. What happened next is much clearer. As the cloud contracted, it began to spin faster. A figure skater does the same thing when pulling in her arms. The total angular momentum is conserved, so a smaller object rotates more quickly. The collapsing cloud also flattened. Collisions among particles reduced motion above and below the main plane while allowing material to continue orbiting in the same direction. What had once been an irregular cloud became a broad, spinning disk. Most of the mass fell toward the center. Pressure and temperature rose. Deep inside the growing central body, temperatures eventually became high enough for hydrogen nuclei to fuse. Fusion released enormous amounts of energy. A star switched on. The sun was born. The sun took almost everything. Today it contains about 99.86% of all the mass in the solar system. Every planet, moon, asteroid, comet, and human being came from the tiny fraction that remained in the disk around it. That leftover fraction did not look impressive. It was a thin mixture of gas, ice, and dust. Yet all 8 planets would be built from it. We know disks like this are real because astronomers can see them around young stars today. The ALMA radio telescope array in Chile has photographed broad disks of material surrounding newborn stars. Some contain bright rings and dark gaps. In many cases, those gaps may be places where forming planets are gathering material or disturbing the disk. When we look at those distant systems, we are not merely looking at strange stars. We are looking at possible versions of our own past. But a disk of dust is not a planet. How do particles smaller than smoke become a world nearly 8,000 miles wide? The first step was surprisingly gentle. Tiny grains collided and stuck through electrostatic forces. The same kind of attraction that makes dust cling to a screen helped the first particles gather. Clumps became larger clumps. Dust became grains. Grains became pebbles. Then the process encountered a problem. Once objects reached certain sizes, collisions no longer guaranteed growth. Pebbles could bounce apart. Larger pieces could crash hard enough to fragment. Gas drag could also make them spiral toward the young sun before they had time to grow. Scientists sometimes call parts of this the bouncing barrier and the meter-size barrier. The simple story dust sticks to dust until a planet appears is not enough. One leading explanation involves concentrations of pebbles within the disk. Gas and dust did not move in perfectly smooth circles. Turbulence, pressure variations, and a process known as streaming instability could gather enormous numbers of small solids into dense regions. Once a concentration became massive enough, its own gravity took over and collapsed it into a larger body relatively quickly. The details are still being studied. But the result is clear from asteroids, meteorites, computer models, and observations of other star systems. The disk produced countless solid bodies, some miles across and others much larger. These are called planetesimals. At that scale, gravity changed the game. A larger planetesimal pulled in more surrounding material. As it grew, its gravity became stronger, which allowed it to grow even faster. The winners accelerated away from the rest. Over hundreds of thousands to millions of years, the inner solar system filled with planetary embryos, objects perhaps comparable in size to the Moon or Mars. This was not a quiet assembly line. Their orbits crossed. Their gravity disturbed one another. They collided, merged, shattered, and collided again. For tens of millions of years, the region around the young sun was less like a finished clockwork system and more like a demolition site, in which the debris was slowly building larger worlds. Earth is one of the survivors. It was not made in a single moment. It is the combined remains of many smaller bodies. Every major collision added mass, changed its rotation, and released heat. Some objects struck gently enough to merge. Others hit with enough energy to melt vast regions of the growing planet. Location also mattered. Near the young sun, temperatures were too high for abundant water ice and many volatile compounds to remain solid. Rock and metal survived more easily. That is why Mercury, Venus, Earth, and Mars became dense, rocky worlds. Farther out, beyond what scientists call the frost line, ice was more plentiful, and the giant planets could grow around much larger stores of solid material. Somewhere in the inner disk, one planetary embryo continued to consume its neighbors. This was the proto-Earth. It looked nothing like the world outside your window. There were no blue oceans. No green continents. No breathable sky. Large objects continued to fall from space. Some were the size of cities. Others may have been the size of countries. Each impact converted motion into heat, just as a piece of metal warms when repeatedly struck with a hammer, but on a planetary scale. Gravity added more heat. Material falling onto Earth accelerated before impact. Compression heated the interior. Radioactive elements, including short-lived isotopes that were more abundant in the young solar system, released additional energy as they decayed. The young planet became hot enough to melt extensively. Scientists think early Earth experienced one or more magma ocean stages, periods when a large fraction of its outer layers was molten. Exactly how deep these oceans were, how long they lasted, and whether the entire surface was continuously molten are still debated. The Hadean Earth was probably not one unchanging ball of lava for 500 million years. It may have alternated between violent melting events and surprisingly rapid cooling at the surface. But after the largest impacts, the site would still have been almost impossible to recognize as Earth. The surface glowed. Rock behaved like liquid. A thick atmosphere of vaporized and volcanic material surrounded the planet. The familiar blue and white world lay far in the future. This molten state was destructive, but it also allowed one of the most important events in Earth's history to occur. Drop metal beads into a container of thick mud and they sink. They are denser than the material around them. Something similar happened inside the young Earth. Dense droplets of iron and nickel moved downward through molten silicate rock. Countless streams and blobs of metal descended toward the center, releasing still more energy as they fell. They gathered into Earth's core. Lighter silicate material remained above and became the mantle. Even lighter and chemically distinct material eventually contributed to the crust. Earth separated into layers, a process called differentiation. This happened remarkably early. Isotope evidence suggests that much of Earth's core formed within the first few tens of millions of years of the planet's growth. In a life story lasting 4.54 billion years, Earth established its basic internal anatomy while it was still an infant. That event continues to affect us. Elements that bond readily with iron, including much of Earth's original gold and platinum, tended to follow metal toward the core. Their scarcity in the crust is partly a consequence of that early separation. Some precious metals now near the surface may have arrived or been redistributed later, but much of Earth's original supply is far beyond our reach. The core is enormous. It begins about 1,800 miles beneath the surface and extends to the center, with a radius of nearly 2,165 miles, or about 3,480 kilometers. It is not all the same. The outer core is liquid metal. The inner core is solid, compressed by immense pressure. No drill has reached it. The deepest borehole humans have ever made barely scratched the crust. So how do we know the core is there? Earthquakes illuminate the planet from within. When a powerful earthquake occurs, it sends different kinds of seismic waves through Earth. Some waves can move through solids and liquids. Others, called shear or S waves, cannot travel through liquid. By measuring when waves arrive at stations around the world, where they bend, where they speed up or slow down, and where they disappear, scientists can map boundaries deep below the surface. S waves do not pass through the outer core. P waves bend sharply there, creating a shadow zone on the opposite side of the planet. Other seismic paths reveal a solid inner core within the liquid outer layer. In effect, every large earthquake performs a planetary scan. Earth's total mass provides another clue. A planet made only of surface-like rock would not be dense enough to match the mass we measure from its gravity. Something much denser must be concentrated inside. Seismology, gravity, laboratory experiments, meteorite chemistry, and physics all converge on the same broad picture. A rocky mantle surrounding a mostly iron core. By this stage, young Earth had acquired a layered body. But it had not yet acquired its most important companion. Look at the Moon and it seems ordinary only because we have seen it all our lives. In reality, it is unusual. Compared with its planet, Earth's moon is very large. Mercury and Venus have no moons. Mars has two tiny, irregular moons only a few miles across. Earth has a spherical satellite more than 1/4 of its own diameter. Why? The decisive evidence came from the Apollo missions. On 6 landings, astronauts collected 842 pounds 382 kilograms of lunar material and returned it to Earth. Scientists have been studying those samples for more than half a century. Moon rocks carried 2 important clues. Many were depleted in substances that evaporate easily, suggesting that the material had experienced extreme heat. At the same time, several isotope ratios, most famously oxygen isotopes, were remarkably similar to those found in Earth's mantle. The Moon appeared to have been born in a violent, high-temperature event, yet built from material closely related to Earth. The leading explanation is the giant impact hypothesis. About 4.5 billion years ago, near the end of Earth's main growth, a planetary body roughly the size of Mars struck the proto-Earth. Scientists call the impactor Theia. It probably did not hit head-on. A glancing collision would have blasted enormous amounts of hot rock into orbit while allowing much of Earth to remain together. Around the battered planet, the debris formed a glowing disk. Rock vapor condensed. Molten droplets collided. Gravity gathered the orbiting material, and from that wreckage the Moon emerged. The broad idea explains much the Moon's large size. Its relatively small iron core, its depletion in volatile materials, and its close chemical relationship with Earth. But the simple version is not the final answer. Earth and Moon rocks are so isotopically similar that scientists continue to debate exactly how much material came from Theia. How thoroughly the collision mixed both bodies. Whether Earth was spinning unusually fast, and whether more than one impact may have contributed. The giant impact is the leading framework, not a perfectly reconstructed security camera recording. We know a great deal about the crime scene. The exact sequence of the collision is still being investigated. Whatever the details, the event transformed both worlds. It likely melted much of Earth again. The young Moon also possessed a magma ocean. Earth had survived its largest known collision, but once more its surface had to begin cooling from extreme heat. This time, the solar system was slowly becoming calmer. The largest planetary embryos were disappearing into planets or being ejected. Impacts continued, sometimes catastrophically, but the intervals between the greatest collisions grew longer. Earth could radiate heat into space faster than new impacts delivered it. A dark crust began to form across the surface, much as a thin skin forms on cooling lava. It cracked, sank, remelted, and formed again. The first crust may have been repeatedly destroyed, which is one reason so little survives. Yet solid ground was beginning to exist. The atmosphere was still alien. Free oxygen, the gas that now supports our breathing, was essentially absent. Volcanoes and the hot interior released water vapor, carbon dioxide, nitrogen, sulfur compounds, and other gases. The young sun was fainter than it is today, but greenhouse gases helped retain heat. As Earth cooled, water vapor could begin to condense. Rain fell. This was probably not one uninterrupted storm covering the entire planet according to a simple cinematic schedule. Conditions varied. Water condensed where the surface was cool enough, collected, evaporated, and fell again. Impacts could temporarily boil portions of it away. Volcanoes continued to add vapor. Over long spans of time, however, liquid water accumulated in low regions of the crust. The first oceans appeared. Where did all that water come from? The old answer was that comets delivered it. The modern picture is more complicated. Some water was likely inherited by the material that built Earth and later released from the interior through volcanism. Additional water and hydrated minerals arrived in asteroids, especially bodies chemically related to carbon-rich meteorites. Comets may also have contributed. Isotope measurements suggest that asteroidal material was probably more important than the classic image of icy comets filling an empty ocean basin. The exact proportions remain uncertain. Earth's water has been melted, evaporated, buried, cycled through the mantle, and mixed for billions of years. The question of where the oceans came from is a full mystery of its own. But evidence suggests that water appeared surprisingly early. To find it, we return to Earth's missing first chapter. Earlier, we said that almost no intact rocks survived from the planet's first 500 million years. That is true. But a few microscopic fragments escaped destruction. In the Jack Hills of Western Australia, ancient sedimentary rocks contain crystals smaller than grains of sand. They are zircons, hard, chemically resistant minerals that can survive even after the rock in which they first formed has been eroded, buried, heated, and destroyed. Finding them requires patience. Researchers crush large quantities of rock, separate dense minerals in a process not entirely unlike panning for gold, and inspect thousands of grains. Most are younger. A few are extraordinary. The oldest known Jack Hills zircons are about 4.4 billion years old. Earth was only around 150 million years old when they formed. A crystal barely wider than a human hair had preserved a piece of history that an entire planet had lost. Zircon is an exceptional archive because it accepts uranium atoms into its crystal structure when it forms but generally rejects lead. Over time, the trapped uranium decays into lead, creating an internal clock. The crystal also preserves chemical clues about the magma, crust, and possibly the water present around it. Some analyses of oxygen isotopes in these ancient zircons suggest that liquid water interacted with rocks at or near Earth's surface before the crystals formed. If that interpretation is correct, then parts of Earth had cooled enough for crust and liquid water by about 4.4 billion years ago, far earlier than the old image of a planet remaining continuously molten for its entire youth. We should be careful. A few microscopic crystals cannot provide a global photograph. Their original rocks are gone, and scientists continue to debate what environments produced them. Early Earth may have moved repeatedly between calmer periods and devastating impacts. A cool region with water could exist even while other regions were violently active. Still, the zircons changed the picture. The Hadean Earth period, named after the underworld, may not have been an uninterrupted hell. It was certainly dangerous and dynamic, but it may also have developed crust and oceans with surprising speed. As the interior continued evolving, another planetary system came to life. Motion in the electrically conducting liquid outer core generated a magnetic field through a process known as the geodynamo. Exactly when a stable early dynamo began, and how it changed through time, remain active questions. But Earth's magnetic field became an invisible structure extending far beyond the surface, deflecting much of the charged particle flow from the Sun. That shield is still being generated beneath our feet. Thousands of miles below us, liquid metal continues to move. The differentiation of the young planet is not merely an event frozen in the past. Its consequences are active every time a compass turns north and every time Earth's magnetic field interacts with the solar wind. This is what makes the science of Earth's beginning so remarkable. No single object tells the whole story. Meteorites reveal the age and original ingredients of the solar system. Telescopes show disks and forming planets around other stars. Physics explains how clouds collapse and rotating matter flattens. Computer models test how dust, pebbles, and planetary embryos behave. Earthquake waves expose the core. Gravity constrains the hidden mass. Moon rocks preserve evidence of a giant impact. Zircons carry chemical memories of the first crust and perhaps the first oceans. Each clue is incomplete. Together, they describe the same broad sequence. A cloud collapsed. The sun ignited. Dust gathered into planetesimals. Planetesimals collided into planetary embryos. One of those embryos became Earth. Heat melted and separated the young planet into core and mantle. A giant impact created the moon. The surface cooled. Water condensed. Crust and ocean began to stabilize. The broad outline is strong, but science does not pretend that every frame is settled. We still do not know exactly what triggered the birth of the sun. The leap from pebbles to planetesimals is still being investigated. Models disagree about the giant impact. The timing and extent of magma oceans remain uncertain. The sources of Earth's water are still being measured. New meteorites, new lunar samples, new asteroid samples, and better simulations can change important parts of the picture. That uncertainty is not a weakness. It is the reason the story is still alive. We can now return to the blue ice of Antarctica, where this journey began. The fist-sized black stone is physically the same object it was at the beginning of our story. But it no longer looks ordinary. That meteorite and Earth came from the same ancient cloud. They were made from the same original mixture orbiting the newborn sun. They are like two pieces taken from the same batch of dough. Then their paths separated. One piece became part of a growing planet. It melted, separated into layers, suffered colossal impacts, formed oceans, moved continents, and continually remade itself. The other never became a planet. It remained small, cold, and comparatively unchanged, preserving conditions that the larger world erased. One changed so completely that it lost the memory of its birth. The other stayed small enough to remember. That is why the oldest surviving account of Earth's beginning was not found deep inside Earth. It fell from the sky. And the story is not only about a vanished past. Its machinery is still running. Meteorites still land on Antarctic ice. The moon still circles us as a monument to the greatest collision in Earth's history. Liquid metal still moves in the outer core, maintaining a magnetic field born from the planet's internal separation. The crust still breaks, sinks, melts, and returns. Earth is still editing its own pages. The ground beneath us is not a finished object. It is one frame in a transformation that has continued for more than 4.5 billion years. The next time you look at the moon, remember that you are seeing the remains of a planetary collision. The next time you stand on ordinary soil, remember that its atoms once drifted through a disk around a newborn star. And the next time you see a small dark meteorite in a museum case, Remember that it may be older than every mountain, every ocean basin, and every intact rock on Earth. Our planet forgot the moment it was born. But a stone from the sky remembered for it.